All right, good morning. Today we are going to see the geometry of quantum states, the qubit in particular. Now, let's look at classical bits. Well, classical bits are binary 0, 1. Uh, and the physical implementation can be a stored charge in a capacitor. Quantum bits well, essentially it's a 2D vector space. That is a column vector, and I can have a orthonormal basis. So this is a Hilbert space, mind you. Orthonormal basis where by convention I have and this guy. This is also called as the computational basis or the standard basis. So what are the examples of this? Spin half, where the upspin is the 0 and the downspin is 1. It can also be, so the example depends upon the degree of freedom we are considering, whether it's a spin degree of freedom of an electron or let's say a photon polarization. Where your right circular light could be 0 and 1 could be your left circular light. A two-level atom where your 0 could be the excited state and 1 would be the ground state. So how to visualize a qubit? Well, one way to visualize a qubit is, let's say, consider an arbitrary state. Vector in a two-dimensional Hilbert space. So I have this guy, and let's consider normalized vector. So I have a normalization condition as well. So I have 3 independent parameters. That's the surface of. So immediately when I consider 3 independent parameters, say this was a complex number, this was a complex number, each of them are 2 degrees, but they are tied by a relation. So in some sense I have 3 independent parameters, and this reminds me the surface of a sphere. I'll come to, actually this reminds me of the entire sphere, but let's see what do I mean by this. So let me represent the qubit as cosine theta by 2, 0, plus E iota phi sine theta by 2, 1. Mind you, the overall phase doesn't really matter, so I could just might as well instead of these two things. So this qubit is equivalent to something with an overall phase of, I don't know, phi 2. So an overall phase in front of a qubit doesn't really matter, but the relative phase between the 0 and the 1 is going to matter, as we shall see. So by convention, I pick theta to have a range between 0 and pi, and the phi, the phase, is ranging from 0 to 2 pi. So that defines me of I have two parameters now, theta and phi. This is actually theta, and that defines for me the surface of a sphere over here. I have the x-axis, I have the y-axis, and I have the z-axis. So this is my 0, where I have the theta and phi now are the polar angle and the azimuthal angle. So theta is 0, which is also Ez, or it's my spin up, or it's my representation for the right circular polarized light. The orthogonal state, mind you, is 1. 1 and 0 are the orthonormal bases, but on this block sphere, the sphere is called the block sphere. So orthogonal states are geodesics on the block sphere, and this is minus Ez, or in other words, it's the downspin, or it's going to be represented by the left circularly polarized light. In general, any state on the surface of the sphere, as we have already seen, is going to be cosine theta by 2, 0, plus e to the power of I phi sine theta by 2, 1. Unit vector in the direction n. That's how I represent it by n. So this is going to be, in general, some, let me label it as n, this state over here. And as you can see, this guy is going to be something diametrically opposite to it. This is going to be minus n. Or this guy is going to be sine theta by 2, 0, minus over here. Mind you, in this convention I have n to be orthogonal to minus n. That's just a way of representation. It's not the minus sign, it's the label. So that's going to be 0. They are orthogonal states. So that's how I represent all the points on the sphere, surface of the sphere. It represents the state of a qubit. So as you can already see, unlike the classical bit, which was either a 0 or a 1, a qubit has infinite possibilities, all points on the surface of the sphere. Okay, so this is called the block sphere. For light, it is called something called as the Poincare sphere. It's the same thing for the state of the light. So once again, I have the axis, and well, let me just label other states on this qubit also. So if this is EY, this guy was minus EY, which was, if you do the math, and this was EX, and this was then certainly EX and minus EX. So yeah, EX would be okay. So this is the right circularly polarized light, and what we have here is the orthogonal state to it is the left circularly polarized light. On the sphere, it's 0, 0, minus 1. In what was the x-axis, you have minus 1, 0, 0, and 1, 0, 0, which is going to be linear polarization, horizontal linear polarization, and this was a vertical linear polarization. So for example, the block vector typically is the degree of freedom is the spin half particle. This is the up spin. This was the down spin. For a photon polarization degrees of freedom, this is the left circularly polarized, right circularly polarized, vertical polarized, horizontal polarized. And of course, the y-axis would correspond to the vector 0, 1, 0 on the sphere, which is 45 degrees linear polarization. This would be 0, minus 1, 0. And these three guys, S1, S2, S3, the three components I'm talking about, this is called as a Stokes vector. And the three components here, or any n over here, this is called as a block vector, generically, the block vector. So these are just definitions, just a way of representation of states. Certainly, each of these directions also defines the direction of the projector. So I can have a projector in the n direction, and that's going to be essentially, if you do the math, it's going to be cosine squared theta by 2. I'm just going to expand my generic state in the n direction, this guy, and I'm going to obtain, when I evaluate the outer products, That's going to be this guy. So this is a short form of writing a projector, which is going to be where I mean n dot sigma. Sigma are the Pauli matrices. So this is a shorthand notation of writing a projector in this particular form. That's just evaluated by the outer product here. Expanding this guy. This is just a math. There's no deep concepts out here. So I'll just say, what do I mean? I'm just expressing, when I express these guys 0, 0, 1, 1 in the standard 0, 1, 1, 0 computational basis, I express that in terms of the Pauli matrices, where my Pauli matrices are sigma x, which is also called as sigma 1, or also called as the x operator, which is nothing but this guy, and in the matrix representation it's this guy. Sigma y is this guy, and sigma z is this guy. Okay, so what are the properties of these Pauli matrices? So essentially, I request you guys to play around with Pauli matrices and outer products in the block sphere just to get a feel of these things. There's also going to be some homework problems regarding that. So properties of Pauli matrices are going to be, well, they are Hermitian. So you can of course verify them. They are Hermitian as well as unitary. Also, so when they are Hermitian as well as unitary, this implies that the square of them is identity. The product of two Pauli matrices is this is the asymmetric symbol, which essentially means, well, you start with 1, 2, 3, that's 1, and essentially this is equals to if they are in the cyclic order, or this represents a permutation of these guys, then you get a minus sign. And any two indices, just check the definition of this guy on Wikipedia if you want clarification. And if any two indices are equal, this is called as the Levi-Cavita symbol. If any two indices are equal. Okay, so this essentially is some of the properties of Pauli matrices which one should keep in mind. Uh, so this is P is called also as the uh, parity of permutation. Is the number of pairwise interchanges of indices necessary. Indices necessary to unscramble into the original order of psi 1 to 3. Okay, so what does that mean? Well, that just means that sigma 1, sigma 2 would come out to be iota sigma 3. Remember this expression. This is the Kronecker delta function. Is equals to minus sigma 2, sigma 1. Sigma 1, sigma 3 equals to minus iota sigma 2 minus sigma 3 sigma 1, and sigma 2 sigma 3 equals to iota sigma 1 equals to minus sigma 3 sigma 2 sigma 1. And essentially the idea is that the all products of Pauli matrices can be reduced to a single matrix, and this is the usual commutation relation. This guy. So for example, sigma 1, sigma 2 is going to give us, and so on and so forth. Sigma 3, sigma 1 is going to give us. These guys are traceless. Trace of again where nx sigma x plus ny sigma y plus nz sigma z. Well, they are orthogonal, so remember the trace inner product we can define. This is the orthogonality relation. Operators identity sigma 1, sigma 2, sigma 3, they form a basis for a four-dimensional operator space. So that any operator can be written as this guy. So which also means where I have the same convention A sigma is just ax sigma x plus ay sigma y plus az sigma z. So sigma is essentially called as the Pauli vector with three components. It's a vector where the entries in the row are the matrices. So in that sense, let's say I could represent any operator A as some coefficient multiplied by the identity matrix and components of your usual ordinary vector ax, ay, az multiplied by the Pauli vector. So my projector is nothing but, you can work this out over here, and there's some more properties of the projector where I have this guy as this is the same representation as the outer product, remember, and I also know that these projectors in opposite directions are going to form a complete set of orthogonal vectors, which is going to be the identity. So I can combine 1 and 2 to show that this guy is equals to which is nothing but the eigen decomposition. Remember the spectral decomposition? This is the eigen decomposition of this guy. In other words, n is an eigenvector with an eigenvalue 1, and this guy is over here. If A is Hermitian, well, one can define a unit vector. Here now n is not an operator, it's a unit vector. And with that regard, I can regard the operator A in terms of the unit vector. It's the magnitude of the vector times this guy. So in other words, in this way, the eigen decomposition of A is going to be with these eigenvalues. So these are the eigenvectors and these are the eigenvalues. Okay, so some more properties. Maybe this was the eighth property. If I exponentiate this iota n sigma gamma, that is nothing but this guy. So what about my observables? Well, if the system is in the state, let's say in a state n, and let's say there is a measurement of this observable. Well, the eigen decomposition of this observable is nothing but this guy. So any direction you measure, either you're going to get a +1 eigenvalue or a -1 eigenvalue, and the probability, so the probability, let's say, of +1, that is getting this guy, is just the inner product squared, which is, so I have a state on the block sphere in the n direction, and I am making a measurement on this projector. The probability I am getting the state m with an eigenvalue of 1 is just going to be related to the dot product of these two vectors, and of course I'm going to get a -1 with probability this. Okay, now let me consider this particular operator. Let's say I have an operator the Hermitian operator. Once again I define the unit vector n. Now I have a unitary matrix. I can write it down as this guy, which gives me what? When I expand it, it just gives me, because I commutes with this guy, so I can just expand it as this guy, and I get so this is also known as the rotation operator. What this essentially means is that this unitary, in fact, you can notice that I in general write the unitary matrix as an exponential of I times the Hermitian operator, and my Hermitian operator was this guy. I plugged in the values, so the bottom line is I am representing any particular unitary matrix as an exponentiation of a Hermitian operator, which can be viewed as a rotation. A rotation along the axis n by an angle of theta. So u can be viewed as rotating the vector on the Bloch sphere by theta. So I have some vector my initial vector, and I'm rotating, let's say, it about the x-axis. This is going to rotate by an angle given by theta, and that operation is going to be given by a unitary matrix. And in fact, I can write down any unitary matrix over this two-dimensional vector as a rotation about some axis. That's what we've shown it over here. There was nothing in particular about A's, but for the fact that it's Hermitian, and I can write down any unitary matrix as E of iota times H, where H is a Hermitian matrix. So generally, any U can be construed as a rotation by an angle of theta about an axis in the direction n. So once again, we use our identity, one of the results. This was, I should use it to be equal, cosine gamma plus iota n sigma sine gamma, and in general, using that, it's going to be, I'm just plugging this guy over here. Now gamma is theta by 2. That's going to give me in fact, you can multiply this guy to any vector, and the vector you're going to get is a vector which is going to be rotated on the Bloch sphere. The rotated, I call it theta, by angle theta about axis given by n. So it's nice to see the action of unitary operators on the Bloch sphere as rotations of these vectors, the vectors themselves to be points on the space, the projectors themselves also to be geodesics, points on the space, and in general the properties of the Pauli matrices, and so on and so forth. So I'll give you some homework problems so that all this is more concrete in your head. But essentially, we'll be using this geometry a lot. And essentially, whenever someone talks to you about a qubit, a quantum bit, this Bloch sphere, where all states on the surface of the sphere are permissible values of a qubit has infinite number of possibilities, as you can already see, unlike a classical bit. So we'll continue more properties in the next lecture, and we'll start with our simple quantum algorithms. Now, slowly we have all the pieces. But once again, the request is to try and practice this yourself. It's going to be more fun. Thank you.